In this section, we're going to get started with polynomial factoring by the method of factoring out the greatest common factor, or the GCF method. So first we want to talk about a few sign properties. It's first often useful to write something like x minus 2 as x plus minus 2. Mathematically, these are the same thing, but some settings warrant the change. Next, we're going to talk about the strategy of factoring out a negative 1. This can be a very powerful tool because we can use it to flip the sign of everything in an expression. If you think about it, everything has negative 1 as a factor. 2 can be written as negative 1 times negative 2, x can be written as negative 1 times negative x, and negative 7 can be written as negative 1 times positive 7. So suppose that I take the expression x minus 2y plus 4xz minus 7y. A lot of terms, but let me factor a negative 1 away from each and every one of them. When I do so, I get the following expression. Now that negative 1 looks like a common factor, I can bring it to the front and leave everything inside the parentheses, and instead of writing it as negative 1 out front, I'll just write it as a minus sign. Note that we're just explaining the process here. It doesn't always take this much detail in practice. Normally we go from the starting expression to the end expression. We just factor out a minus 1, flip all the signs of the terms therein, and tack that negative 1 outside a set of parentheses. We can even see that if we were to redistribute this negative 1, we would land exactly where we started. Now let's motivate the idea of factoring out the greatest common factor, or the GCF for short. Let's start with the expression 12x to the fifth minus 4x squared plus 8x cubed times z. We're going to go ahead and break this down in full detail, meaning that we're going to write every number factored out and every copy of x and z that we can see. What we want to do is figure out what all these terms have most in common, and we're talking numbers and number of variables. As we scan through each term, we can see that 2 squared is present within each term, as well as 2 copies of the variable x. This means that within each term, we're going to factor away the term 2 squared times x squared. And we want to keep track of what we're factoring away from. So once we have all these terms split up, we can bring that 2 squared times x squared out to the front and leave x cubed minus 1 plus 2xz behind. We can even simplify that 2 squared as the number 4. You can almost think of this like it's a reverse distributive property. I have found the greatest common factor within each of the original terms, and I factored it out to the front. Let's look at a couple examples. We'll first start with 3x cubed y minus 9x to the fourth y plus 12x cubed y squared. In terms of variables, we can see that each term has at least one copy of y and at least one copy of x, so we want to factor out as many commonalities as we can. Likewise with the numbers, everything here is a multiple of 3. So, breaking this down, we can see that we have common factors of the number 3, common factors of x cubed, and a common factor of y to the first. Meaning every term has at least one factor of 3, has at least 3 copies of x, and at least one copy of y. But I can't go beyond this. I can't factor out a 9 because 9 is not present in the first term. I can't factor out 2 copies of y because not every factor has at least 2 copies of y, and so on. But putting all this together, I have found a GCF of 3x cubed times y. I'll group all of my terms so that I can reveal that greatest common factor and keep track of what values I will be leaving behind. Whenever I'm factoring a number out, you can almost think of it like division. But once I have grouped that 3x cubed y in each term, I can factor it out to the front, and I'll leave behind the quantity 1 minus 3x plus 4y. For our next example, look at 2xy squared z cubed plus 7xy squared z squared minus 2xyz to the fourth plus 8xyz. Even though this is 4 total terms, it's just giving us practice with finding that GCF. So let's talk about it. Each term has at least one copy of x, y, and z present, but it doesn't look like I can increase any power of x, y, or z. In terms of numbers, it doesn't look like I have a common number, because 7 is an odd number, and even though I have a factor of 2 in the 3 remaining terms, I can't say that 2 is a common factor. So we can conclude that at least one copy of x, y, or z is present in every term, so I have a GCF of x, y, z. So let's start rearranging our terms so that that x, y, z reveals itself. And once I've done that, I can factor it out to the front, which means I'm going to leave behind 2yz plus 7xy minus 2z squared plus 8. Couple of things to think about here. When I'm factoring numbers away from other numbers, it's almost like division. In the first example, when I factored the 3 away from 9, I left behind a 3. When I factored that 3 away from 12, I left behind a 4. Again, because it's like division. In terms of exponents, notice that my exponents have been decreasing. When I factor an x away from itself, I leave no x's behind. When I factor a y away from y squared, I leave behind y to the first. So my exponents will decrease, and they'll decrease in the amount that I'm factoring out. For our next topic, we'll talk about factoring by grouping. Notice that the expression a cubed plus ab minus a squared b minus b squared has no GCF. So we need something different. But what happens if we were to group the first and second pair of terms? By examining this, we can see that the first pair of terms, a cubed plus ab, has a GCF of a, and the second pair of terms, a squared b minus b, has a GCF of b. So I'm going to factor an a and a b away from these first and second groups respectively, and what I get is a times a squared plus b minus a squared minus b. And what I want y'all to notice is that the quantities inside the parentheses are almost the same. They would be the same if the negatives in the right quantity weren't there. However, like we talked about before, I can factor out a -1 and change all the signs. Doing so is going to get me a times a squared plus b minus b times a squared plus b. So by factoring out a -1, I see a squared plus b show up in two places, meaning that I can factor it out as though it were a greatest common factor. Doing so is going to get me the answer of a squared plus b times the quantity a minus b. And this is factored by grouping. It ends up being a pretty nice strategy if the polynomial is set up correctly. The main idea is that if I group the first and second pair of terms and factor out their GCF, I may leave behind a common factor within both. For our next example, we'll look at x squared minus 3xy plus 3xy minus x. Again, I have no GCF among the entire term, so I'm going to group the first and second pair of terms. The first pair of terms has a GCF of x, and the second pair of terms has just a GCF of 1. So I'm going to factor it in the following way. I'm going to get x times x minus 3y plus 3y minus x. It's okay if I have a GCF of 1 because it just means that I group that term within parentheses and I don't factor anything out yet. But now let's look at what we've got. The term x minus 3y and 3y minus x, again, are similar. They're almost the same, but not exactly. I need them to be exactly the same to factor them out as a GCF. But this is why the power of factoring out a -1 is so important. If I were to factor out a -1 from 3y minus x, it would change all the signs therein, and I guarantee it's going to make that second term look exactly like x minus 3y. So let's see this in action. First, let me rearrange the order of the terms in that second quantity. I'm going to write that as -x plus 3y. Now I'm going to factor out that -1, and this is going to give me x times x minus 3y minus the quantity x minus 3y. Since I have two copies of x minus 3y, I can factor that out front, and I leave behind the quantity x minus 1. Therefore, as my final factorization, I get quantity x minus 3y times quantity x minus 1, and we're done. For our next example, we'll do 3ac minus 5bd plus bc minus 15ad. Now, if I were to group the first and second pair of terms as the expression is given to us, I'm not going to find a GCF within both. So I'm going to rearrange or flip those two middle terms. I'm going to rewrite this as 3ac minus 15ad minus 5bd plus bc. I'm allowed to rearrange terms in a polynomial expression like this as long as I bring the signs along with. Now notice that the first and second group of terms finally do have GCFs. That first group of terms has a GCF of 3a, and that second group of terms has a GCF of b. Let's go ahead and factor out those GCFs to get 3a times the quantity c minus 5d plus b times the quantity -5d plus c. Do I have to factor out a -1 again? I actually don't in this case, because even though the terms aren't arranged the same within each parentheses, everything has the correct sign. So all I'm going to do is flip the order of negative 5d and c to get 3a times c minus 5d plus b times c minus 5d. Finally, I can factor out the common c minus 5d to get the final answer of c minus 5d times 3a plus b, and we're done. So always pay attention to whether or not I simply just need to rearrange terms or if I actually need to factor out a negative one.